10.5 Lesson 4, Area of a Polar Region. Our objectives for today are 1. You'll be able to find the points of intersection of the graphs of polar equations. And 2. You'll be able to find the area of a region bounded by polar graphs and radial lines. And of course, the same vocabulary we've been having, radial line. We look at number 17 for our first objective. The instructions are find the points of intersection of the graphs of the equations, and the two polar equations we have are r is equal to 1 plus cosine of theta and r is equal to 1 minus cosine of theta. So let's look at their graphs first as sketched on Desmos. And in the textbook you're also given a figure of the graphs. When you look at the graphs of the two polar equations, you can see 3 points of intersection. So we have one here with polar coordinates r theta, where r is 1 and theta is pi over 2. We have one here with polar coordinates r theta, where r is 1 and theta is 3 pi over 2. And we have a point of intersection at the pole. And of course, at the pole r is 0, and theta could be different values for the angle of rotation from the polar axis. And let's think about how we found coordinates of points of intersection with graphs of rectangular equations. Suppose we have the parabola given by y is equal to x squared, shown here in red, and the line given by the graph of y is equal to x plus 2, shown here in green. Now on the graph we can see that there are 2 points of intersection, and they are marked as negative 1, 1, we'll call that point A, and 2, 4, we'll call that point B. You could have also found the coordinates or the x-coordinates of these 2 points of intersection by recognizing that these are points that the two graphs have in common. So the ordered pairs are common solutions of the two equations. You can find the x-coordinate of each point of intersection by setting the two rectangular equations equal to each other and solving for x. So you're going to write x squared is equal to x plus 2. And the reason why we can do that is at the points of intersection, of course, the 2 points of intersection have the same y coordinate for points on both graphs. So the y coordinates will be equal when you have points of intersection. So that is why we set the equations equal to each other and solve for the x coordinates of the point of intersection. So you can do that by solving this quadratic equation. And of course you can factor it. And when you factor it, you get x plus 1 times x minus 2. Set each factor equal to 0. And you get the x coordinates of the 2 points of intersection. So we can do the same thing with our polar equations to find the coordinates of the points of intersection. However, in addition to that, you have to be careful with polar coordinates for reasons that we will see. But you can do this to start the process. Find the points of intersection of the graphs of the equations. So just like we did with the same problem with the rectangular equations and their graphs, we're going to set the 2 polar equations equal to each other and see which of the 3 points of intersection that we see from the graph we will get doing the problem like this. So you can solve for theta subtract 1 from both sides of the equation, and you will get cosine theta is equal to negative cosine theta. Add cosine theta to both sides of the equation, and you'll get 2 cosine theta is equal to 0. Divide both sides of the equation by 2, you get cosine theta is equal to 0. And that happens when theta is pi over 2 plus pi n, where n is an integer. So if you choose a couple of values for n, like n is equal to 0, you get pi over 2. If n is equal to 1, you get 3 pi over 2, and so on. So this tells you the theta values of 2 of the 3 points of intersection. This one here, theta is equal to pi over 2, and this one here, where theta is equal to 3 pi over 2. But it doesn't tell you that there is a third point of intersection. And we want to think about why that happens. The reason why that happens is these 2 points, let's call these 2 points A and B, they occur on both graphs at the same value of theta. So when you set the 2 polar equations equal to each other and solve, you will get the theta values for both points A and B. However, the third point, let's call this C, the point at the pole, it occurs at different values of theta for the 2 polar equations, and that is why you don't get the third point of intersection doing the problem this way. You can click on the link on the upper right to see the demonstration on Desmos showing that we do not get point C at the same value of theta for both polar equations. So as we just saw with our Desmos demonstration, the point at the pole occurs at different values of theta for the 2 polar curves, and that is why you wouldn't get that by taking this algebraic or trigonometric approach to finding the coordinates of the points of intersection. So on the red curve, which is the graph of the polar equation r is equal to 1 plus cosine theta, this point at the pole on the red curve occurs when theta is equal to pi, because we would have cosine of pi is -1 and 1 plus -1 is 0. So we'll have 0 pi on the red curve, which gives us a point at the pole. But on the blue curve, we would get a point at the pole when theta is equal to 0, because cosine of 0 is 1 and 1 minus 1 is 0. And because we get points at the pole for different values for theta on the 2 polar curves, we would miss that particular point of intersection if we relied only on this algebraic approach. So you have to look at the graph to make sure you get the coordinates of all points of intersection. In addition to looking at the graph, you can do this algebraic approach to verify the coordinates of some of the points. Now we'd like to take a look at an example from the textbook for our second objective. You'll be able to find the area of a region bounded by polar graphs and radial lines. The focus of our lesson will be writing the definite integrals that would give us the area of the region of interest. And as far as evaluating each definite integral, I will mention briefly how it's done, and you can look at the example in the textbook for that. This is example 3 from your textbook. Find the area of the region common to the 2 regions bounded by the following curves. In other words, the graph of this polar equation will be a circle, so you will have the inside of the circle, and the graph of this polar equation will be a cardioid, and you'll have the inside of the cardioid. But the instructions for the problem are find the area of the region common to the two regions bounded by the following curves. In other words, you want to see where the inside of the circle will overlap with the inside of the cardioid, and that's the region whose area we want to find. So we need to begin by looking at the graphs of these two polar equations so we can see the region whose area we're trying to find, and from there we can think about what the integrals should be and how we need to divide that region that we're interested in finding the area for into subregions, and then write a definite integral for each subregion. So here we're looking at the circle and the cardioid. The circle is in red and the cardioid is in green. The equation for the circle is r is equal to -6 cosine theta. And of course, the region that we're interested in is the region common to the two regions bounded by the following curves. And as I said before, the first region is the region inside the circle. The second region is the region inside the cardioid. But we want to find the area of the region that is inside both the circle and the cardioid. So let's see where that region is. So first I will shade the region inside the circle. So that would be all of this. So this is the region that is inside the circle. Next, I will shade the region that is inside the cardioid. So let's look at that. So that's going to be all of this. This is the region that is inside the cardioid. But what is the region that we're interested in? The region common to the two regions bounded by the following curves. What that means is the region that is both inside the cardioid and the circle. And that region would be over here that I am now shading in gold. So this is the region that is inside both the cardioid and the circle. So I'm going to erase what I should not have as a part of my region. So I will go ahead and get rid of all of this. That's not a part of the region that we're interested in. This part that I'm erasing now, it's inside the cardioid but not inside the circle. So that's not a part of the region of interest either. Inside the cardioid but not inside the circle. So the region that we're interested in is the gold region. And let's do it this way. Let's go ahead and maybe shade the parts that we don't want, just for simplicity. I am now shading the parts that we do not want. Okay, these are the parts that we don't want. So we don't want the part that I am shading in gray. We want the part that's shaded in gold. But I'm going to erase that so we can sort of focus on it better. So the part that I am showing you now, we want to find the area of that region, not the grayed out parts. So how do we find the area of this region? One thing that you may notice right away when you look at the figure here is that there is symmetry for this region. And the symmetry is with respect to the line containing the polar axis. Of course, here's the polar axis, and the line containing the polar axis would continue to include the radial line theta is equal to pi. So above this line, you have half the region, and below this line, you have the other half of the region. So you can find the area of just half of the region and multiply by 2, and that would give you the area of the region common to the two regions bounded by the following curves. So one thing that you might notice is that there is this radial line that I will now show you using gold. And the radial line is theta is equal to 2 pi over 3. So here's the radial line. Theta is equal to 2 pi over 3. And the significance of that radial line is it divides the region above the line containing the polar axis into two subregions. The first subregion is bounded by the graph of the polar equation r is equal to negative 6 times cosine theta, which is a part of the circle or an arc of the circle, and the radial line theta is equal to 2 pi over 6. And also we have to consider for what value of theta do we have a point on the circle at the pole. Well, when theta is equal to pi over 2, cosine of pi over 2 is 0, and negative 6 times 0 is 0. So we have the point r theta on the circle with theta is equal to pi over 2 and r is equal to 0. So that's a point at the pole for the circle. Why do we need to know that? Because that's going to help us to determine what the limits of integration should be. So this particular subregion that I am now going to shade in red, it is bounded by the two radial lines. Theta is equal to pi over 2 and theta is equal to 2 pi over 3, and the graph of r is equal to negative 6 times cosine of theta. So I can begin by writing a definite integral that would give me the area of that subregion, the red subregion. And of course, remember, as we've learned, how do you find the area of a polar region? You use this integration formula, 1/2 times the definite integral from alpha to beta of f of theta squared d theta. So what you need for the red region, and by the way, this is going to give you only half of the area, and of course, here's what we need to do. So to find half of the area, or area divided by 2, we need the area of the red region, and we need to add to that the area of the blue region. And what is the blue region? The blue region is right over here. You can see that it is bounded by the radial line. Theta is equal to 2 pi over 3, and theta is equal to pi, and the graph of r is equal to 2 minus 2 times cosine theta, which is right over here. Perhaps I should have done that in green, but I did it in blue. So let me go ahead and just change the coloring here to blue. So the point that I want to make is that half of our region of interest is above the line containing the polar axis, and that half of the region can be further divided into two subregions, the red and the blue regions, and now we can write a definite integral for the area of the red region and write a definite integral for the area of the blue region, and add those two definite integrals together, and that would give us the area of half of the region of interest, because we're only looking at the portion of the region of interest that is above the line containing the polar axis. There is, of course, the same amount of area below the line containing the polar axis. So once you have the two definite integrals, you would multiply them by 2 to get the actual area of the region of interest. And that is why I have area divided by 2 to signify that I'm only looking at half of the area. So for the first red region, you're going to use the limits of integration pi over 2 and 2 pi over 3. So you have 1/2 times the definite integral from theta is equal to pi over 2 to theta is equal to 2 pi over 3, what would the integrand be? The red region is bounded by the two radial lines. Theta is equal to pi over 2, theta is equal to 2 pi over 3, and the graph of r is equal to negative 6 times cosine theta. So for the polar equation, you need to write negative 6 times cosine of theta, and of course you have to square that, and you have d theta, and you're going to add to that the area of the blue region, and we're going to write a definite integral for that. So we're going to write 1/2 times the definite integral. The limits of integration, you will notice that the blue region is bounded by the graph of the polar equation. R is equal to 2 minus 2 times cosine theta, so that's going to be the integrand, 2 minus 2 times cosine theta, and of course you have to square it. But what would be the limits of integration? You can see that the blue region is bounded by the graph of the polar equation. R is equal to 2 minus 2 cosine theta, and the radial lines, theta is equal to 2 pi over 3, and theta is equal to pi. So that's what we have for the areas of the red and the blue regions. We add them together, we get half the area of interest, and then multiply by 2. And of course, when you multiply both sides of the equation, a over 2 is equal to the sum of the red and the blue integrals. When you multiply both sides of the equation by 2, on the left side you'll just have area, and on the right side, when you multiply each definite integral by 2, you have 2 times 1/2 is 1. 2 times 1/2 is 1, and this is going to be the definite integral that gives you the area of the region that is both inside the circle and inside the cardioid. You can take a look at my Desmos demonstration for the region of interest, and especially focusing on the coordinates of this point of intersection, by clicking on the link. But I also want to go ahead and go over one other thing right here. You can visually see that this is a point of intersection of the two curves. But how do you know that theta is equal to 2 pi over 3? Well, I have the fortune of having a very precise graph, but what you can do is, this is what? What is this? It is a point of intersection of two polar curves. So you can find the coordinates of this particular point of intersection by setting the two polar curves equal to each other. And let's go ahead and look at that now. So we will set negative 6 cosine theta equal to 2 minus 2 cosine theta, and we will solve for theta here. So we will begin by adding 2 cosine theta to both sides of the equation. So when we add 2 cosine theta to the left side of the equation, we get negative 4 cosine theta is equal to 2. Divide both sides of the equation by negative 4, we get cosine of theta is equal to negative 1/2. And what are the solutions of this trigonometric equation? Remember, cosine of theta is the x-coordinate of the point on the unit circle intercepted by the terminal side of an angle in standard position. And you get theta is equal to 2 pi over 3 plus 2 pi n, where n is an integer. You also get theta is equal to 4 pi over 3 plus 2 pi n, where n is an integer. And you can see that these, and when you set n equal to 0, you get 2 pi over 3 and 4 pi over 3, giving us the theta coordinates of these 2 points of intersection between the circle and the cardioid. The other thing that you needed to do was to determine the lower limit of integration for the red integral, which we found to be theta is equal to pi over 2, and that came more from a visual examination of the red region that I am showing you once again here, and making the visual observation that the red region is bounded by the graph of the polar equation r is equal to negative 6 times cosine theta. The radial line theta is equal to 2 pi over 3. But what's the other radial line? We see that here's how you can do it by setting up an equation if you want to do it that way. You're going to see that this particular point on the circle is at the pole where r is equal to 0. The question is, what is theta? So you take this polar equation for the circle, set that equal to 0, and when you do that, you get cosine of theta is equal to 0, and that happens when theta is pi over 2 plus pi n, where n is an integer. And of course, if you choose n to be 0, you get pi over 2, telling you that you get this point on the circle at theta is equal to pi over 2, and this particular arc of the circle is traced as theta goes from pi over 2 to 2 pi over 3. And that is why the limits of integration for the red integral is from pi over 2 to 2 pi over 3, giving us the region of the area of the red region. And for the blue region, you would see that the blue region is bounded by the graph of the polar equation r is equal to 2 minus 2 times cosine theta. The radial line theta is equal to 2 pi over 3. But if you wanted to know that the other radial line should be theta is equal to pi, we can see that it should be from our visual observation, but you will also notice that there is this point on the polar curve with polar coordinates 4, and if you wanted to verify that theta was in fact pi, you could set this polar equation equal to 4 and solve for theta. So when we do that, we will have r is equal to 2 minus 2 times cosine theta, and we will set r equal to 4, and we will solve for theta. So subtract 2 from each side of the equation, you get 4 minus 2 is 2. Divide each side of the equation by negative 2, so you get cosine of theta is equal to negative 1. And of course, the solutions of this equation are theta would have to be pi, cosine of pi is negative 1, plus 2 pi n, where n is an integer. And if you choose n to be 0, you get pi. And that is, of course, the upper limit of integration for the blue integral. So the lower limit of integration for the blue integral is 2 pi over 3. And the upper limit of integration for the blue integral is pi. So we looked at how to find definite integrals to find the area of the region. We paid close attention to finding the limits of integration, and this is what you have, and you can of course go back to the link that I had mentioned earlier for Desmos and click on that if you want to see Desmos' demonstration of what you just saw in terms of explaining the limits of integration and the sub-regions for our region of interest. If you want to evaluate each definite integral, you would need to square, and you're going to have cosine squared, and you're going to have to use a power reducing formula. Here you would have to FOIL, and then you will also have cosine squared in there, and you're going to have to use a power reducing formula, and you can refer to example 3 in the textbook for more on that. So we just looked at an example where you would be able to find the area of a region bounded by polar graphs and radial lines, and we tried to examine that a little bit, a little portion at a time, dividing our region of interest into subregions and then finding the area of each subregion. We also used symmetry to make it easier for us to do the eventual calculation of the values of the definite integrals.